All right, here in this one, we're going to do problem 112, I believe. So this is a non-symmetric bending problem. What it has here is this C channel on its side, or I call it an N channel, and then we have a moment vector here, right? So that means that the bending plane is perpendicular to that moment vector. So basically, here is the bending plane. Let's try to draw that a little more neatly. Okay. And they want you to figure out the maximum stress. So they've already kind of let the cat a little bit out of the bag. The maximum stress will be at one of the corner points. And actually, since the bending plane is sort of this way, it would make sense, or seem logical, that it would be roughly, the neutral axis we haven't quite determined. The neutral axis will not be necessarily perpendicular to this, but it seems plausible that it would be one of these corners and not one of these ones. These will be the intermediate stress corners. Most likely, this will be a combination of tension and compression, and these corners will be the, this will be tension and tension and compression. When I'm talking about that, I mean the bending around the x-axis will be, the bending around the z-axis will be in compression, and the bending around the y-axis will be in compression, likewise here. You don't have to know that yet, but, you can kind of guess at that by looking at the picture, all right? But if you don't, that's fine. All right, we also will need to compute the location of the centroidal axis, this y bar from the top fiber, all right? And also we're going to need the second area moments, the inertia products, the area products around the z-axis and the y-axis. All right, so we need to compute those, all right? So actually, if you look, I posted another video where I did the computation of geometric area properties using an Excel spreadsheet, and actually I used this as an example for computing those. Here's the spreadsheet. So what this tells me, so you can look at that video, or you can do the calculation. I won't go through the calculation again. It's just parallel axis theorem and computing the centroid. This is for the bending around the z-axis. The centroid is 142 millimeters up from the bottom edge, and this is the I about the z-axis. About the y-axis, this is the I, and here's the centroid. It's right in the center. That's what you would have expected anyway. So from that, this distance here, we calculated it to be 142 millimeters. So that means this distance has to be the 200 minus 142, which is 38 millimeters. All right. The I about the z-axis turned out to be 40.7 times 10 to the minus 6 meters to the fourth. And the I about the y-axis is 1.82 times 10 to the minus third meters to the fourth. So obviously there's much bigger bending resistance around the y-axis. Let's make sure I got the number of decimal places right. Oh no, this is actually to the fifth. It's actually, let's do it this way. 0.407 to the minus third meters to the fourth, okay? 0.407 and 1.82. That seems a little more realistic. It shouldn't be off by an order of magnitude. All right. So again, go to that video if you want to see the details of that calculation. All right? I want to focus here more on how to do the actual nomenclature for the bending problem. All right? So let me pull up that little slide. Oh, this isn't in the text, but this is the one that I used in class, right? This gives you the orientation. If here's the bending plane, the angle theta is the angle between the y-axis and the bending plane. Or if you want to do it this way, it's the angle, oops, this angle here is theta as well. It's the angle between the z-axis and the moment vector, right? So if we look at this diagram, here's the z-axis, right? And here is the moment vector. So in fact, this angle here is theta, all right? All right. That's the orientation for theta. Okay. The tangent of theta, well, actually, I really need, well, so the moment in the z direction is the moment times the cosine of theta, okay? So that's 520 Newton meters. The cosine of this angle is going to be negative. It's a angle greater than 90, and it's going to be 12 over 13. That's the cosine of the angle. And that turns out to be, here's my calculator. That is 480 Newton meters, a negative. Okay? So it's going in this direction, right? Negative. And y, the component in the y-axis, is going to be m sine theta, which is 520 Newton meters. The sine of this angle is going to be the rise over the run. It's positive 5 over 13, and that ends up being 200 Newton meters. Okay? So now basically what we're going to do here, we can directly apply the bending equation that we derived in class. But let me just do it a little differently. I think I'll do it for two reasons. One, again, it emphasizes the derivation of this and what's going on. And also will kind of give you a little better feel for why it is we're doing this. So this is really the stress that originates from bending in the y-plane. This is the stress from bending, I should say from in the zx plane. So if I were to look at this section and draw it twice, what we're going to consider here is the superposition of the stresses. Here's the z-axis. Here's the y-axis. So first, we're going to consider this 480 bending moment around the z-axis. So that's, I always have a tough, let's draw this. So it's a little 3D looking. And here is the x-axis. So this would be as if we had a bending that went around like this. Let me get the sign right. It's a minus 480, so that's actually going down this way, right? Where this is 480 Newton meters. All right, so we figure out the stresses in that situation. This is what's giving us that term. And then we're going to superimpose onto that the stresses that we would get. Same cross-section. It's the same picture. Z-axis, Y-axis, X-axis, but then a positive 200 Newton meter bending moment around the Y-axis, or in other words, in the, the ZX plane. So this is the one that puts this side into compression, and this side will be in tension. Likewise, this one will put this edge in tension, and this edge in compression. Call this 1, and this is 2. So this is the picture. This gives us that stress, okay? And that's all that equation is doing, just adding those two cases together. So even if you don't memorize this equation, which is fine, that's not necessarily an equation that we all memorize, you can at least figure it out very easily by just decomposing the bending moment into two components, two problems around the principal axes, okay? Or the axis of symmetry, right? So here, again, if we look at this, here's going to be tension, and then this edge is going to be tension. So that means actually at this point here, B, both modes are in tension. And likewise, at this point here, A, both modes are in compression. All right? So that's why on this picture you can see they've kind of pegged you with the dots at B and A. Probably would have been better if they didn't show that. At these points here, at this point here, we have tension from this mode bending around the z-axis, but we're going to subtract from that the compressive stress that we get here. And likewise, at this point here, this guy is compressive, but we're going to add to that negative stress the tensile stress that results from this side. Okay? So this A and B, those are the points where we're going to have to look and see which one's maximum. Okay. So let's consider those separately. I've got to find a piece of paper I've written on. It's not easy to do here. All right. So let's just consider the stresses from bending, from bending in the YX plane. That's this case 1. That's this picture up here. Can you see it? It's that picture, right? We're going to consider this one. Maybe I'll just put this up here for now. Okay? All right. So the max stress, all right, on this edge, let's draw the picture. Let's be a little careful about our bookkeeping. Okay, in this situation, we know this distance here, this C distance, is the 41, 42, what was it? Oh, I'm sorry, 38, excuse me. That's 38 millimeters, and this distance to this outer fiber is going to be 142 millimeters. And it's not meters, it's millimeters. All right. So let's get the stresses at both the top and bottom. So the stress on this edge, all right, that's going to be a tensional stress. That's the moment 480 Newton meters. That's the M. In this case, the C is 0.038 meters. And then the I, that's the bending around the Z-axis. All right? So that's 0.407 times 10 to the minus third meters to the fourth. Okay? So all I've done here, I'm actually not using this equation, but you can see I've actually ended up computing the same thing as I would get if I did the first term. All right? This is the stress I would get at this top surface. Okay? All right. And it's tension. Okay? The other way you can look at it is I would have had a minus, and this is a minus moment. So it's tension. Now when I compute that, what do I get? 480.038 times 0.407 to the minus third. This gives me 44.8 kilopascals. Now let's also get it on this edge. Okay? So this is going to be, again, minus a minus 480. Now the C distance is a negative 0.142 meters. You can also see, obviously, this is the same sign convention we got before. We assume that this would have been compression by looking at the picture up here, right? But you can see the sign convention also works out. And then I divide by 0.407 times 10 to the minus 3 meters to the fourth. And this now gives me should be a greater stress than it is. 167 kilopascals in compression. Okay? Along this whole edge, that's what we have. We're in compression 167 kilopascals. All right. Now let's look at case 2. Now we're going to consider the bending around the y-axis, or this is the bending in the zx plane. So this is, now we're going to consider this is the sort of case 2 that I drew previously. Still, it's the same picture. Here's the toppled over C channel. Here's the z-axis. Here's the y-axis. And now we've got bending in this plane, all right, such that this side, let's see if we got, what do we get, right? This side's going to be in tension, this is going to be a tension side, and this side will be in compression. So if we wanted to get the stress here, that's going to be that moment, M, which is what, 200. That's the component of M around the y-axis. Now its distance here, this is 0.2 meters over I, which in this case, this is the I about the y-axis. That's the 1.83 times 10 to the minus third. And that gives me a stress of 21.9 kilopascals tension. Now this side is going to be a compressional stress. That's minus 200 Newton meters. Its C distance, I'm sorry, it's a positive, right? Because it's bending around the y-axis. its C is a minus 200 millimeters, or 0.2 meters, over the same thing, 1.83 times 10 to the minus third meters to the fourth. So that's going to give me minus 21.9 kilopascals. So again, you can see this is the point where they're both in compression, and this is the point where they're both in tension, both modes. So at this point here, that's point A, right? Let's first look at point A. The sigma x normal stress is going to be the bending stress from the first mode plus the bending stress from the second mode. Now at A, from the first mode, that's this point here. So that's a minus 167 kilopascals. And then this compressional stress we get on this edge from the second mode is a minus 21.9 kilopascals. So that gives me a total of 189 kilopascals in compression. So that's at A. Now if we do at point B, this point, it's the same deal, but this is going to be from the first mode on this edge, right, because that's where point B is, on this edge, we have a positive 44.8 kilopascals. And then at point B, from the second mode, the bending around the y-axis, I get a minus, I'm sorry, on this edge, it's a positive 21.9 kilopascals, and that gives me a positive 66.7 kilopascals. So in this situation, the maximum stress is here at point A, and it's a compressional stress of 189 kilopascals. Okay. Now let me do it by directly applying this formula. Okay. Now that you kind of see where that comes about, right? Okay. So if we want to get it at point A, let's first consider point A. So let's just click. So now using equation star, where this is equation star, all right? All right, we get that this is point A. So at point A, I should probably put that little picture back up again. Right, we have, it's at the coordinates y is equal to, I don't know, z, we have a minus 0.2, and then the y is minus 0.142. And this here is at z equal to 0.2, and then y equal to 0.038. That's meters, right? Meters, 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 meters. Sorry for being sloppy. It's Friday. Okay, fine. So here we are at point A. At point A, in this picture here, we know that we're going to use y equal to minus 0.2 meters, and then z is going to be set equal to minus 0.142 meters. All right. We plug in these values we already computed. So using this equation, right, the star equation, we move that down here. This will give me that sigma is equal to minus mz, which is a minus 480, times the distance y to that point A. We know that that's minus 0.2 meters, all over Iz, which is the 0.407 times 10 to the minus third. It's meters to the fourth. This is Newton meters here. And then we get plus the y moment, which is a positive 200 Newton meters. The z distance, which is a minus 0.142 meters, over the y second area, which is the 1.82 times 10 to the minus third meters to the fourth. And now if we compute this out, well, let's see, here's the moment of truth. Hopefully I get the same answer. I usually don't like doing these problems where I get the same answer twice because I almost often will get the wrong answer. But let's see how I do. The numbers are the same, so I should get the same answer, actually. And I get 25.200. Wait a second. I get the wrong answer. Okay, I must have did a typo. See, this is why I never do these. All right. This term should come out to be the minus 167. Right? Let's see if I get that. 480.2 times 0.407 to the minus third divide. Oh, I'm getting a different number here. Oh, yeah. Wait. I got these flipped. I'm sorry. I got these flipped. What am I doing? Sorry. For the y-coordinate at this point A, right? This coordinate. The y-coordinate is minus this distance, which is the 142. So this should be minus, I'm sorry. The z distance, right, is minus 0.2. I have these backwards. Did I get that wrong back here? Where did I write? I must have. Yeah, I kind of have this backwards. This is backwards. This is the z is minus 0.2. Well, I guess I got it right. And then the y is minus 0.142. It's a problem with this. I'm used to seeing xy. Okay. So this actually should be minus 0.142 meters. I'm sorry. And this one should be minus 0.2 meters. And you can see that's exactly the same number I got before. Let's try that again. Make sure that that works. I'm sure it will. Right. Now this term becomes 167 kPa, and then this term becomes the 22 kPa, and then actually this is a negative. And this is a negative, so we add those together. I get the 190 kPa. The difference there is just a little round off error, right? All right, now we're going to do point B. All right, so at point B, we're going to use y equal to 0.038 meters, positive, and then we're going to use z equal to 0.2 meters. Okay? Now at this point, the stress is going to be equal, again, minus 480 Newton meters. But then we put in here for y 0.038 meters. And then we put in here for the IZ, it's still the same, 0.07 times 10 to the minus 3 meters to the fourth, plus 200, that's the same, but the only thing different here is we put in for Z 0.2 meters. It's actually the same value, right? So this is going to be the same as this, it's just positive, so that's 22 kPa. And this one is, it's actually the same exact calculation I had before. I mean, I'm going to do the other way, but let me just do it to make sure I didn't screw anything up. And then this becomes 67 kPa. And this I forgot the sign. That's compression and that's tension. It's basically the same results we had before. Just a little, rounded a little differently, right? Minus 189, 190, 66.7 or 67, right? So I get the same results. All right. Let's look at the location of the neutral axis, all right? So here's our theta, all right? Now let's get the location of the neutral axis, all right? So we're going to use, again, this equation, all right? This is the equation that gives the orientation of the neutral axis. So to get the neutral axis, we're going to use that the tangent of alpha is equal to IZ IY, the tangent of theta, okay? Now I want to be a little careful about tan alpha. If you remember tan alpha, there's a little bit of a quadrant issue with the tangent function, right? Tangent is the rise over the run. So here the tangent is greater than 0. Here the tangent is less than 0. Here the tangent is greater than 0, and in this quadrant the tangent is less than 0. Okay? So you have this sort of non-uniqueness with the tangent function with respect to the sine. Okay? So we have to be careful about that when we do these. So this is IZ over IY. Now IZ, we computed before, this is 0.407 times 10 to the minus third meters to the fourth, over the IY, which is the 1.82 times 10 to the minus third meters to the fourth, times the tangent of theta. And if you look at this, tangent of theta is rise over run. So the rise of this angle is 5. The run is minus 12. So tan theta is minus 5 over 12. And so that gives me minus 0.0932. Okay, that's the tangent of alpha. All right, so now when I take the tan of that, you want to be careful. That gives me 0.093, what is this? 93 radians. And so that would either be since it's positive, that's either giving me this angle. Well, we should be careful about that. Well, there's Z and Y, and we're defining that positive angles in this sense, right? So in fact, if I have an angle here, this could be alpha, or it could also be this alpha, the one that's 180 from it. But actually, in fact, it doesn't really matter because those define the same neutral axis, right? So that's alpha equal to 0.093 radians, which in degrees is about the same. I'm sorry, that's 5.3 degrees. Okay? So that's saying that that angle is 5.3 degrees. So if I go back and look at this picture, right, alpha is actually positive 5 degrees in that sense, okay? So remember, alpha is the angle from the z-axis up to the neutral axis, right? So that's about 5 degrees. So that's the location of the neutral axis. Okay, we have one sign error I screwed up here. You look back here, right? This was the negative tangent angle, so this actually became a negative. This becomes a negative. So actually the way I drew this is incorrect. It's a minus angle. So we define the positive theta this way, so it actually goes that way. It's about 5 degrees. So it actually looks something like this. This is actually the neutral axis. That's the neutral axis. That angle there is 5.2 degrees. Okay? And again, that would make sense. You can see this point actually a lot closer to the neutral axis. So that's why that stress is lower. If you go from here, the farthest distance out is this one, but this one's actually even farther, and so that would be the max stress. And that's where you get the max stress. Okay? All right, thanks.